is the last part of this class, part B, B.3, examples of asymptotic notations. In this part, I will give you 9 examples. First few examples very easy, but some later examples relatively harder. So let's see our first example. All right. The first one, 2.B3.1, our part of B.3, our first example. Show that n plus 2 belongs to big theta of n. First, I like you to recall what's the meaning of big theta of n. Okay, big theta, we try to bound our f of n function. N plus 2 is our f of n function. Okay, we try to bound our f of n function from above and also from below. Okay, 2 bounds, upper bound and a lower bound. Okay, so let's start. So when we start, so let's do 1 bound first. The lower bound looks easier, so let's do the lower bound. So why it is easier? Think about, we just drop 2. If we drop that term 2, the whole value becomes smaller, right? The whole function value becomes smaller. So then, less than, okay? Greater than, So n plus 2 greater than n, okay? And we know it's a multiple of the g function, right? Because the g function is n, okay? 1 times n, 1 times g function, So we get the lower bound part. And we need to look at under what condition it is true. N greater or equal to 0, it is true. Although some of you may argue even n equals negative, it is also true, right? Mathematically, when n is a negative number, this inequality is also true, but for our computer science algorithms, in our context, the meaning of n is the problem size. Problem size, right? Our problem size can never be negative. So that's why we only consider n greater or equal to 0. So we don't consider n is a negative number. All right. So after this, so you can see we can get the C2 constant. That's 1. Lower bound, C2 constant, 1. Now let's work on the upper bound. This time, we want to control the original function. Or we want to replace that constant 2 by some multiple of n. Constant multiple of n. So here, we just replace 2 by n. Okay? We want to make the new expression larger than the previous one. If that is true, we need n greater or equal to 2, that condition. If n greater or equal to 2, we have that condition. Okay? The lower one is greater or equal to the upper one. So that's, we get the upper bound, 2n. So n plus n, 2n, the upper bound. Okay? So you get the C1 constant equals 2. At the end, you need to tell me what is the n0. So our n0, the n should satisfy both this case and another case. Put them together, n0 equals 2. So to solve a problem like this, you need to tell me these 3 numbers. N0 number, C1 number, C2 number. Okay? Then I know you solve the problem. Okay, so when you do the work, yeah, try, keep in mind, you need to give me these three things in your answers. All right, that's the first question. The second one, n cubed belongs to big omega of n squared. First, we need to recall the meaning of big omega. Bounded below, right? Lower bound. Yeah. So can we use a constant multiple of g function n squared to bound our f of n function n cubed from below? Yeah. So that is easy, right? That's pretty easy. Yeah. Bounded below, we can do that, right? But you need to tell me when n greater or equal to 0, this inequality is true. Okay? Yeah. So now you can give me the c equals 1 and 0 equals 0. That's it. So for this case, you need to give me these two numbers. Then I treat that you solve the problem. Yeah. All right, the next problem. This one, big theta. So this time you need to give me both upper bound, lower bound, just like our first example. Now, let's do lower bound first. Yeah. Lower bound under what condition? N greater or equal to 0, right? So that's easy. Yeah. And we get it. C2 equals 1. Yeah. Now let's work on the upper bound side. We still replace 2 by n, okay? So we get 2n. Yeah. Then we know n should be greater or equal to 2. Yeah. So then 2n, we take cube of the 2n, we get 8n cubed. Okay? So our C1 equals 8. Okay? So we get these three numbers. C2 number, C1 number, and N0. The last thing is N0. You need to consider these two cases. Okay? Yeah. So N0 equals 2. All right. Yeah. Then, next. Yeah. Why so fast? All right. This question. Okay. Yeah. Log of n belongs to little o of n. When you see little o, you need to take limit. Little o, you need to take limit. All right. So now let's take limit. But when we take limit, there is one thing you should be very careful. Here, this n is a discrete variable. Okay? So it's not a continuous variable. We know a function with discrete variable, we cannot take derivative. Okay? So you should be very careful. If you want to take derivative, you need to use continuous variable. So here our x is continuous variable. Yeah. So we work on a continuous variable. Yeah. All right, so you should be careful. Yeah. When you do your homework assignment, you should be careful on this point. Okay? Based on my experience, many students still work on the discrete variable directly. Okay? Yeah. As I know, yeah, many students still work on discrete variable directly. When they take derivative, they apply on discrete variable on functions with discrete variables. Yeah. In that case, I take 1 point off. Okay? The whole question 4 points, remember? Yeah, I explained. The whole question, no matter if it is hard or easy, I always give 4 points. But if you do not use continuous variable when you take derivative, I take 1 point off. Okay? So here I tell you clearly. Okay? Because the reason is I want to give you the training to do rigorous math, not a sloppy math. Okay? Yeah. So I want you, when I give you the training, you should do the right way, rigorous way, not a sloppy way. Okay? All right. Here, the log, we didn't write the log base, so we treat as a hidden general base, a greater than 1. That general base, yeah, greater than 1. Yeah. So we can do the normal computation. Yeah. All right, so now why we can use the L'Hopital's rule here. So here you can see from this step, I use the L'Hopital's rule, right? But when you use the L'Hopital's rule, you need to check the condition. If it is an indeterminate form, here you can see it is infinity over infinity indeterminate form. The numerator goes to infinity, denominator also goes to infinity when x approaches infinity. Yeah. So we can do the L'Hopital's rule. So we take derivative of x, that is 1. Okay? So that's easy. Derivative of x, 1. Derivative log of x. Many of you may not be able to memorize this formula. So you can do the online search. Okay? Yeah. Derivative of log function. You can find the formula, through online search, or go back to look up in your calculus textbook you used before. Okay? Yeah. So here I wrote the formula here, so you can see this is the formula. Okay? Yeah. Yeah. Then we simplify it, we get this expression. Now, do not use the L'Hopital's rule anymore because it's not an indeterminate form. Yeah, because the numerator, it's a constant. It does not go to infinity. It does not go to 0. It is a constant. Okay? So do not use the L'Hopital's rule. Okay? Now, do the limit directly. When x goes to infinity, the whole fraction goes to 0. The answer is 0. Okay? Yeah. So you'll find the answer in this way. Yeah. That's example number 4. Next example, number 5. Power function. N to the dth power, the power function, belongs to little o of exponential function. This exponential function, we assume a greater than 1. The base number greater than 1. Otherwise, it's not true. Yeah. So greater than 1. And the d number we require greater or equal to, so here, anyway, here we say greater or equal to 1, right? Actually, more general, greater or equal to 0 is also true, right? Greater or equal to 0 also true. When d equals 0, that's 1. N to the 0, that's 1. Definitely it's true, right? If it's a positive number greater than 0, also true. But that one, I will talk about that later. For this question, for example number 5, this one, I want to choose d as a positive integer. As a positive integer. Okay? Here I want to use it as a positive integer for convenience. For convenience. Because this way, our formula is relatively simple. But later, we need to extend it. We want to make it more general. All right. Little o, so we need to calculate the limit. So our goal, try to prove this limit goes to 0. That's our goal. Okay. And here, remember, we use the continuous variable x, not a discrete variable n. Okay, yeah. So you can see, yeah. L'Hopital's rule, because it is an infinity over infinity indeterminate form. Infinity over infinity indeterminate form. Okay, L'Hopital's rule. Yeah. All right. Now we get that. Okay. All right. After this, can we get an answer? Yeah. So we feel still not there yet, because now it is still infinity over infinity indeterminate form. We can still apply the L'Hopital's rule another time. Yeah. All right. And here I want to point it out, from this step, derivative of x to the dth power equals this formula. It's the power rule. Yeah. Derivative. In the derivative, we have the power rule. Power function, right? Yeah. Power rule. The derivative power rule. Yeah. So you can find it. This is, we use the power rule. Yeah. Some students may forget this power rule. Okay. Yeah. Apply it another time, another power rule, another time, we get that. Okay. Yeah. Derivative of the denominator, derivative of the exponential function another time. Here we use the calculus formula. Okay. 2 calculus formulas here. Right. All right. So then we keep doing this L'Hopital's rule until we reach this point. The exponent of the power function reaches 0. Because when we assume it's a positive integer, we can get there. Every time we reduce the exponent by 1, eventually we will reach the 0. Yeah. When we reach the 0, we get d factorial. This time it is not an indeterminate form. It is not a limit, infinity over infinity indeterminate form. So we cannot use L'Hopital's rule anymore. Right? So now let's do the limit directly. Because the denominator, this one goes to infinity. All the other things, other numbers, constant. Okay? Yeah. So you have a constant over infinity, that's 0. So the answer is 0. If the ratio of 2 functions, its limit equals 0, your conclusion is little o. Yeah. So that's our definition, little o. Yeah. All right, so that's example number 5. Next example, example number 6. This time, let's show log base 2 of n belongs to little o of square root of n. Okay. This time, square root of n, is this a power function? It is n to the 1/2 this power. Okay. So you can see this time the power function d is not an integer. Yeah. So later we will generalize this. This is true for d greater or equal to 0. Yeah. Greater or equal to 0. Yeah. Even non-integer, it is also true. So later we can do that. We will do that. Yeah. If we want to prove it, we can do it. Yeah. We can do it. Yeah. We just need to do some special treatment for the fractional part. If it is a non-integer, there is a fractional part. So we need to handle the fractional part with some special treatment. Then we can still prove it. Okay? Yeah, still prove it. Yeah. All right. Now we take this limit, the ratio of these two functions, using the L'Hopital's rule, indeterminate form, infinity over infinity. Yeah. So now let us take the derivative. Yeah. All right. The derivative by the formula. Yeah. Before here we write the power function. Okay. X to the 1/2 power, the power function. Then we take the derivative. The power rule. Okay. This here we use the power rule. Okay. The derivative of log formula. So we get that. Then we simplify the fraction. After simplification, we get this. It is not indeterminate form, so we can take the limit directly, right? Yeah. Denominator goes to infinity. Yeah. So the whole limit is 0. Yeah. So that is question number 6. Number 7. Yeah. Show this. Natural log of n belongs to bigger of n to the dth power, but this d greater than 0. Just a positive number, not necessarily integer. Fraction is okay. Okay? Small fraction is okay. Yeah. Even 0.00001 is okay, right? Because this number greater than 0. Even this kind of small number we put here, it is still true, right? So we want to prove that. It looks hard to believe, right? Yeah. Yeah. Maybe it's hard to believe, but it is true. We can prove it mathematically. Yeah. So let's do it now. Yeah. Doing the limit, we need to use continuous variable. So let's take the limit of this ratio and using the L'Hopital's rule. Infinity over infinity, indeterminate form. Yeah. Now we take the derivative. Okay? Derivative of natural log of x. The formula 1 over x. Yeah. Power rule. This is power rule. Okay? Because d greater than 0, so we can use the power rule. Right? Yeah. And then after simplification, we get this expression. Yeah. Now this is not indeterminate form, so we should not use the L'Hopital's rule, but we can do it directly. Yeah. Because x to the d is a positive number, it goes to infinity. 1 over infinity, it is 0. So we get this limit equals 0 by the definition of little o, we prove it. Okay? Yeah. So that's example number 7. Yeah. Number 8. All right. Number 8, this one a little harder. Yeah. Harder than all the previous examples. Show that n factorial belongs to little of n to the nth power. N factorial. Show that. Okay? Yeah. In order to solve this problem, we need to use a very important formula. Without this formula, nobody can solve, problem. Yeah. Yeah, probably there are other ways, but much more complicated. Yeah. With this formula, it is not that hard to solve. Okay? Yeah. It is called a Stirling's formula. Stirling's formula. In Calculus 2, you may learn Stirling's formula. Yeah, but you can find it from web, Stirling's formula. Okay? It is this. N factorial approximately equal to this complex expression. Pretty complex. Okay? With e, natural log base. Here you can see we use natural log base. We use pi. Okay, and we also use square root. See, pretty complicated. Yeah, but it is a nice approximation of n factorial. Otherwise, it is very hard to approximate n factorial. Okay, yeah. All right, but the problem here is this approximately equal this sign. We know they are close, but it is hard to use this kind of expression to do calculation. We like to use inequality, so we can work on it. But this one's a little hard to work on it. Okay, so we need another version of the Stirling formula. That is this inequality version. Okay, n factorial, we have a lower bound approximation like expression and upper bound approximation expression. Then this new expression much easier to use. Yeah. All right, so let's do the work here. Yeah. Excuse me. All right. Yeah, so this question, yeah, we write in this way. Yeah. We do formula transform like this. Yeah. You can see n to the nth power we divided by here. N to the nth power do division to, yeah, like that. So we get this inequality. After that, now we are ready to take the limit. Okay, so we take limit on this inequality. Okay, yeah, everywhere we take the limit. Yeah, when we take the limit, remember, greater than sign becomes greater or equal sign. Greater or equal sign. So that's the way when we do the limit, we need to add that equal back in. Yeah. Otherwise, we miss the equal case. Yeah. All right. When we do that, so now, what is this limit? What is this limit? Can you see that? Right? So here, using our previous example, we can get both limits equal to 0. Why? If we just go back to check our example number 5, we have this, right? D, okay? N to the D, this power function, D equals 1/2. Okay? D equals 1/2. Okay? Little o over a to the nth power, this a equals e, right? Natural log base. Okay? Yeah. So here you can see if we use that result for the general case. Here we use the general case. D, remember, we only need D greater or equal to 0. That general case. Then this limit equals 0. This also equals 0. Okay? Now, our conclusion, we use the squeeze theorem or sandwich theorem. Yeah. So when you learn calculus, so you may see this theorem. Sometimes people call squeeze theorem because you squeeze the middle part from the two sides. Yeah. Both sides 0, then the middle part limit must be also 0. So you squeeze way to force the middle part, its limit also 0. So that's the squeeze theorem. Yeah. But some other people also call the sandwich theorem. Yeah, because here shaped like a sandwich. Anyway, you just take your favorite name to call it. Okay. Yeah. All right. So we solve problem number 8. Then the last one, problem number 9. Yeah. The last one, yeah. The problem is long, yeah, but we can solve it quickly. Yeah. All right, so for each of the following functions, so I give you A, B, C, D, E, 5 functions, indicate the class big theta of G of N. So you need to tell us a simple G function as its growth function. So big theta of G as its growth function. All right, and the requirement, the simplest G possible in your answer. Yeah. So let's do it. Okay. A, I give you this function. B, this function. Yeah. So I do not read the whole expression. C, this long expression. Okay. D, like this. Yeah. E, the last one, we use the floor function. This is the floor function. Okay. Floor function. So you know the meaning of floor function, right? So we drop the fraction part. We only keep the integral part, integer part, but we drop the fractional part. Yeah. All right. So let me do the, solve these quickly. Yeah. All right. One by one. The first, let's try to get a dominant term. Plus 1 minor term we can ignore, right? So if you drop that plus 1 minor term, you have n squared, then you take 10th power, you get n to the 20th power. That is your growth function. So you get that expression. Okay? So B, you also take the dominant term first, right? Then this 10 you need to drop. Yeah. Because when you look at the growth function, you do not include the constant multiple. Constant multiple you can drop. Okay? So here we drop this constant multiple 10. Then we take square root of square cancel out. So we get n. The growth function is n. Big theta of n. All right, the third one relatively more complicated, so let's do at the end. Yeah, let's try to do easier first. Yeah, E, that's easy, right? Because this one greater or equal to log 2n minus 1, right? Yeah, and we know this minus 1 is a minor term we can ignore. Yeah, very small, we can ignore. So then you just keep this. Yeah. LG, LG, sometimes people write log base 2. So in computer science context, when people write LG, that means base 2. In math, when people write LG, that means base 10. Okay? Because in math, the most frequently used base for the numeral system is 10. In computer science, most frequently use the base, binary, right? Yeah. So that's why here we use 2. Yeah. All right. D, yeah, because comparing with exponential function with base 3, the first term is too small. Base 2. The first 2 is base 2 too small. Okay? You can also look at, if you look at the ratio of this, and if you do the limit, that is 0. Right? If you look at that, that's 0. So the first term comparing with the second term, the limit goes to 0. Right? The limit is 0. So that's why we can ignore the first term and we only keep the second term. The second term we can write big theta of 3 to the nth power function. Not power, exponential. Yeah. Exponential function, but power of 3. We can call power of 3. Yeah. All right. The last one, that log one. Yeah. All right, so let's simplify that. Okay, we can bring this exponent number to the front, so we get that. Okay, yeah. And the second one, n over 2, we can write log of n minus 1. Okay, now you can see, because the constant is not important, we can ignore that, right? So this constant we can ignore, so we get n squared, right? So the second term, n squared log of n. The first one, n log n. So definitely the second term is dominant. So we should take the second term. Yeah. Okay. So the answer is big theta of n squared times log n. Yeah. So that's the way we get all the growth functions. Yeah. Although the original form looks very complicated, but if you know which term you can ignore, which term you cannot, but you need to simplify it, then you can find the answer for questions like this. Yeah. At the end, the last step, I want to remind you this formula, the change of base rule in log. Yeah. Log base A, function of B, you can change its base from A to C. Yeah. So definitely all positive. Okay. Yeah. Definitely positive, but not equal to 1. Okay. If the base is 1, not well defined, right? C also greater than 0, and C not equal to 1. Then it is true. No. This is the change of base formula. Yeah. Later, we may need to use this formula several cases. Yeah. Yeah. All right. So we complete this last video.